Hello everyone, my name is Berat and I'm also an undergraduate student in ODTÜ in Physics and Computer Engineering departments. Hopefully I will graduate from physics this semester, but we'll see. So firstly, let me apologize for the inconvenient way of us doing it. I mean, it would be way better if we had done it face to face and you would get more from it and from me, but what can we do? Okay, let's begin then. So our first topic in this video is Deutsch algorithm, and then we'll talk about its generalized version, Deutsch's algorithm. And we'll basically just, after a quick review, see how we can implement these algorithms with the Qiskit tools that we have. Okay, so as a quick review, Deutsch algorithm. In Deutsch algorithm, we had this like oracle function that implements a binary function, and this binary function we called is constant if it maps 0 to 0 and 1 to 1, and we call that it's balanced if it maps 0 to and 1 to different values. For example, a balance function, as an example, is just an identity function or a not operator. Okay, so now I have defined this oracle1 function, which takes as argument a quantum circuit object. It doesn't return anything, but what it does is basically it appends these gates to this quantum circuit, which basically implements this oracle, does the thing of oracle, what we expect the oracle to do. Okay, so these functions are defined in this oracles.py function file, which is located at the same location as your notebooks. So running this code segment basically runs that code, and you basically also have that functions defined. Okay, so let's get to it. So before we start doing this all circuit things, we first need to import the necessary modules from Qiskit. Okay, what do we need? We obviously need a quantum register, a classical register, a quantum circuit to implement all this, and we will get our backends from AR, and we need the execute function to execute it. It's also a nice idea to import this plot histogram function because it gives a nice inherent way of plotting the results that we have. Okay, our circuit will consist of two qubits. One of them is the play qubit that we have, and the other one is the ancilla qubit. Okay, so we initialize this quantum circuit and name it QC. Nothing fancy. So remember, our algorithm was we basically apply a Hadamard gate and put our qubit into superposition of all possible state, which is 0 and 1. And also we need to initialize our ancilla qubit into minus state before applying the oracle. Remember, minus state is the, let's say, eigenvector or eigenfunction of this oracle. And then we apply these Hadamars back to our qubits to see the result, and depending on our result we said our function is balanced or our function is constant. Okay, so there's nothing to it. We basically apply Hadamard gate with this h function, and we apply an x and a Hadamard gate to the second one. Okay, and afterwards we apply our oracle function, call our oracle function, which implements this oracle things, and then we apply Hadamard and measure. Okay, let's see our circuit before moving on. As you can see, there are like things in here that I've also written here, but I didn't talk about them. So if, for example, Qiskit has done with this qubit and you want to measure it at the end, right after the job is done, like this qubit is done, Qiskit will go and measure it, because qubits have what we physicists call a very low decoherence time, or in other words, they just go bad really quickly. So Qiskit wants to, in order to minimize the errors and increase fidelity, just measures them as soon as they're done, their job is done. So putting a barrier prevents that from happening. Well, it doesn't like do anything, it just makes them, our circuits, look better. Okay, so let's run our circuit and look at our results. Okay, we run our circuit and what did we get as our results? 1 0. So this means we get 1 in our qubit and our oracle function is balanced, right? No, because remember, Qiskit used the reverse ordering for their qubits. That is like if your qubit structure is this, then this qubit corresponds to this index and this qubit corresponds to this index, and the reasoning is this is basically is ordered from least significant digit to most significant digit from up to down. So this gives us an intuitive way of representing these qubits, playing with them using this reversed ordering. So keep that in mind. So with that in mind, that means we got 0 as our measurement result for this qubit, which means our function, our oracle function, is constant. Okay, so we talked about this, like this is oracle, it does this, but how do we actually define the oracle? Like if you were to write down the circuit for the oracle, how would you write it down? Well, to write down a constant oracle, you don't really need to do anything. Because remember, when you have like this oracle, it basically adds a plus or minus sign depending on which value that state is mapped to. Okay, so for example, if 0 is mapped to 0, that means 0 state will get a -1 to the 0, that is a plus sign in front, right? And if 1 is mapped to 0 again, it will again get a plus sign in front. Well, if they are mapped to not 0 but 1, they will just get minus signs in front, but it will not change anything for us when we do the measurement, because all that will happen is just simply it's a global phase and we measure it, we will not see it. So we don't really need to implement anything for it. But I just written down some garbage code for you to see. But important thing to notice here before we move on, I kind of enclose this circuit into this black box, and in order to do that, what I need to do is I can like initialize a quantum circuit, for example, just by giving some arguments to it, and right after giving those arguments and defining the circuit, I can actually convert it into a gate. Okay, so this quantum circuit object has this attribute called toGate. This basically converts it to a gate. But to a gate, to append this gate to our quantum circuit originally, we also need to give inputs to the gate, right? So what this does, this function does, is it takes this quantum circuit object for at this moment it's like this object. It creates this object, calls it oracle circuit, and it converts this oracle circuit into a gate and it appends to it. But we need to connect these qubits into the corresponding 0 and 1 connections, right? So this guy in here achieves that. It basically says, okay, map 0 to 0, 1 to 1. For example, if we had written the other way, it would mean you map 0 to 1 and 1 to 0 and etc. Okay, it will become a little more clear once we move forward. Okay, after applying this, as you can see, we applied the Hadamard and measured and whatnot. Okay, it's really easy to see that you can just write a constant function without doing anything. But the question is, how can you write a balanced oracle function? Okay. Now, I will not give the answer in here. I will give it in the Deutsch because it's more general. So I want you to think about this. If you can finite transfer, just write it, try it. If you can't, don't worry about it. Once we talk about Deutsch algorithm, it will be way more clear for you.